Using differential equations. What is the point? The math used behind differential equations involves integration, differentiation, DEs, and simple algebra. DEs were used with the invention of calculus by Newton and Leibniz in 1671. Jakob Bernoulli proposed the Bernoulli DEs in 1695. DEs are used widely in mechanics and physics today. Differential equations can be defined as a mathematical equation in a function that is related to one or more of its derivatives. They are generally represented as rates of change, as can be seen in these graphs here. Differential equations arise from the fact that many relations between variables depend on the rates at which the variables are changing, that is, derivatives. An equation that involves derivatives is called a differential equation. The answer of a differential equation is a function, not a number. A differential equation shows the relationship between a quantity and its rate of change. For example, Newton's rate of cooling, which can be seen from this graph here, with temperature over time. You cannot calculate discrete values with differential equations, and you cannot set a value based on a rate of change, that is differential. Solving differential equations results in function of the dependent variable, without any differentiations. You can then solve the function to obtain its discrete value. There are two main types of DEs, first order and second order, which include variable separable, integrating factor, complementary solution, and
Hello there, I'm going to be talking to you about the real-life application of differential equations in engineering. Woohoo, let's do it. So differential equations are very important in the real world and play a vital role in construction. We'll get into that soon. Engineers need to design products that meet design requirements and specifications. The solution must be cost-effective, efficient, and best resolve the specific issue. So if this engineer here has a small hole in the wall, how is he going to patch it up? It must be cost-efficient and effective, so we'll put a bit of filler in rather than two huge planks of wood. I think that's a bit more efficient. So here's a little example problem. UOW is in need of a new math classroom and they're going to build it out of wood. The new building is going to be on wooden stilts and the location is above the duck pond near the library. Okay, so here's our new building proposal. Differential equations come in handy here because the design must meet certain criteria. The floor of the new math building must be strong enough to hold its contents of desks, chairs, people and computers, all these things here. It must also be sturdy enough to walk on safely. Wood can be a flexible material and strong too. The floor doesn't have to be very thick to hold the small weight of what's in the building. But if the floor is too thin, it may be flexible and deflection of the floor may occur when people are walking on it. Oh dearie me, don't want any of that happening, do we? Oh no, no. So we can use differential equations to calculate the deflection of beams with a load on them. It's very important in engineering to meet the requirements of a product in every way. If the beams in the floor of the new math classroom deflect too much, it'll be more of a trampoline classroom where students will bounce on the springy deflection of the beams. This is very undesirable for the intended purpose, and the calculations done to avoid this issue is with differential equations. Oh, look at this student bouncing around on that classroom floor. Yeah. So the deflection of the beam is found by integrating the moment equation twice. It's a form of a differential equation to get the deflection.